So welcome everyone. We have the pleasure today having with us Professor William Edmonson. He's from the North Carolina State University, right?
Actually, A&T State.
State University.
Because there is a North Carolina State University.
Okay, which is another one.
Which is another.
All right. Okay. From that university. All right. And Professor Edmonson is with us at Theop with a Fulbright scholarship. Is now finishing a 3-month stay, essentially working in the LSTS, so the laboratory, systems laboratory, essentially for multi-agent underwater vehicles, essentially. And also aerial, so combination of multiple agents. And the interests of Professor Edmonson are focused on small satellite systems. So you have been working on the communication for clusters of small satellites,
yes,
and in the design of the process itself, and how to enforce a proper design from the beginning to enforce correct design, right? So proved by construction.
yes.
All right, so thank you very much for being with us. We are eager to hear your talk, and then at the end we'll have a discussion. Thank you very much.
Okay. Obrigado.
Welcome.
Bom dia. I have been trying to learn Portuguese.
All right.
And I actually took a class. Pouco. But yeah, it's actually been a great 3 months. Learned a lot, enjoyed being here, working with the students and faculty over at Felt. And yesterday I actually gave a similar presentation to the science and the computer engineering faculty, or computer science faculty. Can't get those two confused. Down at the other campus, CUP.
The nice campus.
The nice campus, the one next to the botanical gardens. I don't know why they put engineering schools away from everybody. Nobody likes us, we're the stepchild. So what I want to talk to you, or at least briefly, is some of the research that I'm doing, particularly around small sats, but can actually be extended to autonomous vehicles, and it can be even generalized to just cyber-physical systems in general. So I'm going to discuss a little bit about my research center at North Carolina A&T. My research on model-based systems engineering, particularly the formalization of the design process. I also wanted to talk to you a little bit about my work in intersatellite communications based around using visible light. We've actually had several papers on just in general how to go about designing for intersatellite communications, but specifically I hit upon this idea, or stole this idea, using visible light. And then something that I just kind of recently got into, but I think is very, very important as we move forward, not only in the satellite business, but also any autonomous vehicle, any cyber-physical system, and that is, how do we design for resiliency? And I just gave a talk at the NATO Advanced Research Workshop that actually was held in Norfolk, Virginia. And my talk was on using small sats as being part of the critical infrastructure of a nation, but also the importance of resiliency and how we can use small sats and design those for resiliency. Just to give you a little bit of background, I was born in Detroit, Michigan. Whatever you heard about Detroit, don't believe it. It's actually a very good city. It's like I guess it has that feel of Porto, you know, without the other crap that goes on. But if you want a city that, you know, it's really family, but also in family, we get pissed off at each other. Guns are a little too available, so, but a lot of creativity is going on there. I mean, between the music and the automobile industry is still going strong. That's still pretty much the center. And so, growing up in Detroit, I actually went to General Motors Institute, which is now General. So I'm real ensconced in the automobile world, or have been growing up. And sort of moved to space, but still I understand the automobile. I'm still follow F1. But what was interesting was I actually got a dual degree in both mechanical engineering and electrical engineering. Don't ask me why. That's one is difficult enough to try to do two. It's suicidal, so I was one of the few that actually survived. Then I went on to Georgia Tech to get my master's completely in electrical engineering, mostly in signal processing and signal process controls and computer engineering. And then went on to NC State, which is the one in Raleigh, which is their premier engineering school. So when people talk about North Carolina schools, you might always hear about UNC Chapel Hill, but Chapel Hill does not have engineering at all. They have, well, one is biomedical, but I'll just leave it at that. No, it's kind of a funny story because I wanted to go for my PhD in biomedical, and my advisor, he kind of cussed me out a little bit and said, no, you want to go to one of the traditional and then do biomedical. And that was actually very good advice, because really it boils down to, you know, you get your degree, this is for graduate students, in one of the traditional fields, and then you can go off and specialize. So either mechanical, electrical, chemical. I won't say anything about industrial, because there's a running joke, at least in our among students, industrial engineers are easy industrial. But we won't go there. So in terms of my research, it's basically since getting my master's, it's been in the area of signal processing and communication, a little bit of control, a little bit of computer engineering. Then over the last 10 years, as I got into the small sat world, I also got into systems engineering. And I've actually become somewhat passionate about systems engineering because at the undergrad or at the graduate and undergrad level, and seeing how students build small sats, there is no systems engineering process. And having gone through NASA and General Motors, systems engineering is like, you have to know how to design. And, you know, you have to do it cost effectively. And so I said, this is an opportunity. It still has not changed. You know, a lot of the departments or colleges who have systems engineering programs, they're sitting off by their side, off to the side, and not really spreading. So I have my own view on what systems engineering curriculum should be. And one of the things is that you should not teach systems engineering to undergrads. You teach them design. But until you've gone through a design process or several design processes, you really don't understand systems engineering. You know? And so that's my take. So the research center, we can think of it as, just in terms of its vision, is just developing a center to provide technological emission design solutions for the small sat world, particularly in observing the Earth. In terms of its mission, I always wanted to build an international R&D center. It's kind of been a dream of mine. And me being here was part of that, because I'm hoping to develop long-term collaborations. So I'm still open to that. Love to come back, spend 6 months here, 6 months in the U.S. Just throwing that out there. So what was the motivation? In the systems engineering world, industry is going away from the document-centric onto what is called model-based systems engineering. And because what we're trying to do is, or what I'm trying to do is kind of a system of systems approach to small satellite design, where I have multiple satellites that could be heterogeneous. How do you design to that? And because you do have to understand things like interoperability, getting back to resilience, which you'll see what does that mean and how do you design to it. But also, can we design or develop a process in which your design is correct throughout this construction? You also need to manage complexities. How do you do that? Because more and more systems are complex. You can take any Boeing or Airbus plane, and probably what happened with Boeing is that they tried to circumvent some of the processes. That in the 737 is a very old plane. I think that plane is 50 years old that they tried to retrofit and modernize. And it's probably something you should not do. But also being able to make decisions early in the design phase. So as you go down the V, if you're using the V process, from your high-level requirements to, or your low-level requirements to your high-level requirements, can you begin to make decisions? And that way you can actually do redesign very early without, which makes it a cost-effective process. Facilities, or to facilitate communication across disciplines, because most of these designs are actually going to be multidisciplinary, but a computer engineer versus an electrical versus an aerospace, they actually have different languages. And so is there a common language in which everybody can communicate? And there actually is. And it's called systems markup language. So I'll get into a little bit of that a little later. So small set design paradigm. How many of you are familiar with CubeSats? Just one, two. Okay. When I talk about small sats, I should have added in the figures, but I'm talking about basically a satellite that's the size of a shoebox. And so what the smallest, and they actually come in units, one used small CubeSat would be 10 by 10 by 10, 10 by 10 by 10 centimeters on the side. And that can grow to, there's people who have launched 1.5, 2 U's, 3 U's, 6 U's, and all the way up to 12. So one way to designate this in terms of mass is as long as it's less than 180 kilograms is considered a small sat, and that's by NASA's definition. But what that provides is a reduction in overall cost. It's a reduction in launch cost because its mass is much lower than some of the school bus size. It's a lower point of entry. So it's actually, universities can get into this, and many, many universities have. And I think as of over the last 10 years, there's maybe 400. Don't quote me on the 400, but there's more than 200 university led, and actually have launched in space over the last 10 years. And so, you know, if you think about it, I think the costs spread out over a couple of years is anywhere, it's like $1 million. 500 to 500K to $1 million. So relatively, the cost is low. Part of it is that student labor is cheap. So that's one way. The other thing is that in terms of development, we can actually manage this with flat funding. You know, give me X amount of dollars, hopefully 250 to 500,000 a year, and within 3 years with that amount of funding, and I don't have to worry about costs rising. We don't give students raises, things like that. But also what this does, it enables multi-satellite missions. And in fact, there are a few projects, one which is the QB50, which started in Europe. And those were actually 50 CubeSats that have been launched, but it's been spread all over the world in terms of each CubeSat was developed by a different university. Some universities were lucky because they had more funding, and so they had 2 or 3. And so it can be done, and it has been done, and these things have been launched. And so with these multi-satellite platforms, they could be heterogeneous. But one of the good things about this is you actually have increased resolution, both from a temporal standpoint and as a spatial standpoint. Because I can give revisit times, I can design in how many times I need to revisit a particular spot. So if you wanted to, let's say, look at Porto, look at the coast of Porto, you want to do it twice a day or every 30 minutes, depending on what the science is, that will determine how many satellites, but also you have to choose what orbits you're in. So this has been done, and we've actually done a paper study around fire, looking at places in Africa, and we were able to use 6 to 8 CubeSats to detect fire, and it was the resolution was looking at that particular spot once an hour, and all it required was 8. They were spread out, and so it has been done, can be done, and it's doable. And what we're trying to do is a similar type of thing here with the LSTS group. It is designed a mission, and science, around looking at internal waves off the coast of Portugal, and maybe the Azores, and possibly Brazil. But the other thing that's nice about this is that because the missions are shorter, they're going to be 3 years max. Now, if I want to develop another mission, I can actually put in more, the state of the art with the next mission. Now I can begin to use improved parts, learn lessons learned, integrate that in. So it's kind of nice, and this is one of the attributes of small sats. So now I'm going to sort of segue into how do we go about designing in my research in terms of developing a design methodology. So as we know, satellite design, particularly from a student perspective, but even also I've been through 1 or 2 designs at NASA, and part of it is that, particularly industry, everything is risk averse. And so they design to ensure that there is no failure, which means you have a lot of redundancy, you get into cost overruns because something has changed, but also you freeze technology very early. So what might be a 10 to 12 or 10 to 15 year design process, technology is actually frozen the very first year, which means that there is no Moore's law for space. It's always going to be behind. And so what we want to do is to develop this responsive, possibly agile design process. And we're using basically model-based systems engineering to make sure that you're designing right, but also using formal methods to ensure that it's the right design. And then the result of those two should give you this verifiable design process and this corrective construction. The other thing is that I believe there needs to be also a shift in the design philosophy, because most of these systems are going to be or can be categorized as cyber-physical. Because, well, as you might know, cyber-physical systems represents this tight integration between the physical, the networking, and the computing. But in essence, with this philosophy of this belief, you've actually raised the importance in your design of computing. And I don't know if you've ever worked with other or this multidisciplinary design teams, particularly the students, and I don't have to tell you guys this, we can just write a program, we can wait to the end, and everything will work out fine, but almost always using that, it is the computing, it's the programming that gets you in trouble, which actually causes the delays. You need to do that up front, and not at the end. So I'm preaching to the choir. But I've sort of broken this down into philosophy where you think globally as a designer. So you don't so much worry just about your own particular area. You got to know where your area fits. And so that way, when you begin to design for your particular area, you at least have this larger understanding of what interacts with you. And so it's good to keep that in mind because you're not designing in a cycle. But the other thing that we're pushing, or at least I'm pushing, is testing, doing a lot of modeling and simulation as you go through the design process. And this way, because of these tools are actually gotten pretty good, you can then begin to use these simulation tools to help determine if there is a problem, do we need to go do a redesign. But you can do this at each level of abstraction. And so you can do this often and early on. So model-based systems engineering is basically you using models for everything. This will allow you to have a consistent view of the developing system, but it also should offer a reduction in time to integrate these disparate systems. The one thing about model-based systems engineering and why particularly industry is slow to buy into this is there's a lot of effort that's up front in the beginning of the design process. And what they need to understand is that by putting all this effort in the front end, that means at the back end, you don't need to do this. So those redesigns that are very costly are going to be minimal because you've done all the work up front. And again, by using this common language across disciplines, and it's becoming an industry standard, and it's called SysML, Systems Markup Language. Particularly with students, if you're going to go work out in the industry and you're going to be part of the design process, most companies now are using SysML as a way to capture and communicate. So if you go to Airbus, you go to Mercedes or any of the car industry, outside of Paris, in that god-awful place, there are actually a couple of research centers. It's not that bad, but it's in the south of France. This is where it's called Paris-Saclay, and a lot of the engineering schools are moving there. Echo Polytechnic is there, Paris Tech is there, but also all the car company and train companies research center is there. And there's a couple of research groups that are developing SysML. There's actually a free version called Papyrus that you can download, but it comes from, I can't remember the company. Systems X.
Yes. Yeah, it's Systems X.
Systems X, okay. So you know what I'm talking about.
Yes.
Okay. I've actually been there several times, and actually almost got a job there. I didn't know French. So what is SysML? Just in a nutshell, it is a graphical modeling language. It's semi-formal, so it does have meaning. It's notational, so there's a representation of meaning there. But it's not a tool or a language. And a lot of people misunderstand it. It's want to think of it as a tool or a language. I mean, a tool or a methodology. It is a language, like English, but it's a graphical language. And so, just think of it that way. Formal methods, here we're using it not only to sort of prove our process, but we're actually using the tools to help with making sure from our requirements all the way to modeling and simulation that it's consistent. But also as you go down your levels of extraction, that you also have traceability. And I'll get into a little bit of what I mean by particularly traceability, because I think that's important. So a lot of what we're doing is changing this natural language into a logic. And now with that logic, we can then logic representation of the requirements. Then we can use model checkers and their improvers to check for consistency. And so we define this as a verifiable design process. This is actually version 2. We found some holes in version 1, updated it. But it is this integration of MBSE and formal methods using the SysML model types of structure, behavior, requirements, and parametrics. So what are its attributes? As I mentioned before, it combines MBSE to manage system modeling complexity, but also uses formal methods to ensure that the designs are verifiably correct. It consists of a set of levels of extraction, so I'm not violating and still following the V design process. But each level of extraction consists of requirements, models, simulations, and what is the relationship between them. And the relationship between levels of extraction, one can think of as you go down, it's refinement, and as you go back up, it's abstraction. And so in terms of traceability, what you want to show is that refinement and extraction are adjoint, which is adjointness, which is a weak, very weak equivalency. And so in terms of each of our layers, what you have is LN. This is where you begin to start with your requirements. It's written in a natural language, but as you know, natural language is ambiguous. And so how do you go about making that unambiguous? And so we map that into an ontology. And actually we're using an ontology that was developed by David Spivak called OLOGs. but it's O-logs is a direct relationship to category theory. And then from here, we come up with this logical formulation. And in fact, what is interesting is that category theory, O-logs, and the computational category theory we use, the logic that we use throughout can all be based on LTL, linear temporal logic. And so what we have is basically consistency with the theory, with the practice, and also the computational all the way through. So we actually extracted theory to ensure that things are consistent, and if they aren't consistent, we'll go back, rewrite the requirements, and go through this process. The design process, no matter how formal it is still iterative. It's still iterative. And so here we have rules of how to go about extracting the theory. And then once all that's done, then we can actually build the models and do the simulation. And in fact, where the research is now, we can actually use one language to cover all of this. And next couple of slides, I'll sort of briefly go through that. So this is added, if we look at it in terms of between levels of abstraction. So here you have your refinement and abstraction, and if you're edging, then it's traceable. So to facilitate correct through construction design, formal method tools will be used to automatically check for consistency and traceability, where you have consistency across each of the levels, traceability between each of the levels. And so part of my research is in the development of how do we bring about or create, or is there a mathematical foundation to systems engineering? This is some of the work that I'm doing with folks in Paris. But it's, a lot of people are taking pieces of it, but we're trying to look at the whole process. And it's been difficult getting funded to do this. So we use category theory to prove formless of the process. We use computation of category to prove traceability, consistency, but also implement the simulations. And we're using a Haskell derivative. How many of you know what Haskell is? Heard of Haskell? Okay. And so we're using the derivative that's based upon reactive systems. Basically, that's what we have. And so there are one or two variants of that. One is called NAPA, and the other one is monadic reactive programming. And in fact, one of my colleagues that I work very closely with, that was his PhD. And so a lot of this work has actually been coming out of Nottingham. And so that's where he graduated from. And then using the ontologies to facilitate this automatic mapping to logic-based representation from the requirements. So this is just another view, but what's important about this is that you do your requirements that represents a category in terms of the natural language and ontology, but actually you can do the verification, and that represents this process here. But then the modeling simulation, as you go down, actually offers a validation. So you don't have to wait and get the prototype or build the prototype or build the system to actually validate it. You can hopefully do this all along as you go through the design process. And that way you're validating in each step. But it also represents, once I do have to build, now I have to test codes. And I know how to test. So it sort of simplifies a very complex design process. Category theory, just for some of you who might not have heard of category, it is a mathematical study of algebra functions. It's an abstract math, but it is the mother of all math. And so you can actually prove everything else using category theory. And so, you know, it used to be set theory, but now I can actually have category of sets, and prove set theory, category of groups, category of categories. But it's actually very simple. Think of it as you've got a collection of objects, but you have these morphisms between the objects, so you know how information flows, and I'm saying information in a very general way. But as long as each morphism has a source and a target, it is composable, and there is identity. Then you have a category. And so, and if I wanted to do maps between categories, I can do that using a functor. And that functor preserves this word that it just left me. But it actually preserves the structure. And so if I wanted to go from let's say one language to the next, and it meets all these rules, then I can map from Portuguese to English. That should be a very complex system. Portuguese is a very difficult language. So, to show that our process is formal, we've actually looked at the process just from a high-level, abstract level category theory. This is a category, that's a category, that's a category. And we've actually shown that it meets all of the rules. And so the process is formal. But also we've shown that from between the levels of extraction, we've shown that it also meets, it preserves structure as we go from one level of extraction to the next. But it also should preserve structure as we go, and it better preserve structure as we go from requirements to logic to physical implementation. So that was the theoretical part of my talk. Now I want to go into some of the practical stuff, particularly in terms of inter-satellite communication. If we're actually going to build multi-satellite systems, they have to communicate with each other if you really want to enable them to do complex missions. Just like with UAVs or underwater vehicles, if you're going to do a heterogeneous suite or even a swarm, it would be best if they can communicate for things like situational awareness. If there's a failure, you just reconfigure and move on. So we wanted to enable multi-satellite missions, provide coordination amongst the network system, and what this does, it enables the capability for doing reconfigurability, distributed processing, distributed control, distributed sensing, but also in terms of servicing and proximity operations. There's a big push for doing in-orbit servicing, and if I have this small thing that wants to fix this big thing, there need to be some type of communication to enable it. So this is actually a SysML markup of what is called the block definition diagram of the inter-satellite communication system. You probably can't read this, but not only have I had the communication system, but also I looked at the protocols and its relationship to the OSI models. These are the other subsystems, command and data handling, power system, the environment. So I'm able to capture all of this and system L, but also how the information flows. So what I want to do is the LED base, and the reason why it meets the size, mass, and power constraints, a reduced design complexity, it minimizes the line of sight requirements, and here I'm comparing it not so much with RF, but with laser. And with laser communications, a lot of people are looking at that, but it takes very high pointing accuracy, and you might not, or it might be very expensive to achieve that, particularly on these small scales. The spectrum is non-interfering, security, and this is the big one. No licensing fees. So the license is free. You don't have to go to ITU or FCC. So, which is a good thing. And so in that sense, this is kind of the block structure. So it's actually very simple. You got your modulator, and this is at the physical level. You got your LED, the sensor, and actually it's the sensor, this side, that really becomes the more of an issue than the transmission. So we're in space. What do you think is going to be the big noise source in space? Can anybody? The sun. The sun. The sun could actually, depending on how this thing is pointing, it could really overpower the sensor. So, you're all engineers, PhD. What's the best way? What do you do to maybe mitigate some of that?
Communicate during the night.
Well, no, because you still could have sun. Yeah, you could be on the dark side, but you can still be facing the sun.
That's right.
Okay, but it's pretty broad spectrum.
Yeah.
So, I mean, you're getting close.
Maybe there's some gaps in the spectrum.
Exactly. Do you know what the name of those gaps are?
I don't remember, but
Absorption.
Yeah.
Absorption bands.
Yeah.
those diagrams, I
Absorption.
used to see in chemistry.
Yeah. So,
Don't know.
give them names. But you want to transmit what is called the Fraunhofer lines. And this is where the energy falls below 10%. Okay. And that happens to be, it goes along the spectrum, but the one that most interests us, because it has a pretty wide bandwidth, so you don't have to deal with boy, the name escapes me. Really having too much fun here, unfortunately. But anyway, due to the band,
Advanced filters.
hmm?
The filtering it's easier.
No, it's when Doppler.
No.
So you don't have to worry about Doppler because of the bandwidth. And so we're looking at the blue range, so 396, 392, or 393, 396. And if we can transmit there, we still need the filter on the receiver end. But by also putting a hemispherical, you sort of loosen up the requirements on the pointer. Because as long as I'm plus or minus 45 or plus or minus 45, I'm pretty much good. Now, I could be more than that, but let's say plus or minus 45, and if I'm 1,000 meters away, that's a pretty big spread. So we want to also tune the filter on the receiver side to falling within those lines, and this actually results in a natural low background noise. So that's how we're managing this. Now at the MAC layer, this is, I have a PhD student that's presently working on these issues. And what we've decided as of right now is to go with NOMA, or non-orthogonal multiple access. And we're doing this because no modification, because we're using intensity modulation at the physical level. And it's supposedly energy efficient. And what we're really trying to do, if we can get 500 megabits per second, you know, it's not laser, but I think that's good enough for a lot of missions, and able to get even picture data, you know, where you need a lot of data just to get back and forth. The issue still is the space to ground link, but that's also being managed by others. So we're moving away from VHF, UHF to S-band, and even they've been developing X-band. So the downlink data is becoming less, or downlink bandwidth is becoming less of an issue as we move forward. And there are folks that are also looking at using laser for downlink communications. The problem with laser, though, is you still need a nice sized telescope. You know. So now I'm going to move on to just briefly talking about design for resiliency. And I think this is the way to go. And I think category theory is going to be very helpful in proving this out. So we know that small sats can be considered as an integral part of the space critical infrastructure. And actually, both the EU, the US, the UK, all designated space as critical infrastructure. It's important to the health of the nation. So, and there's many reasons why. One of the big reasons is the GNSS, which, you know, position, navigation, timing is all really coming from GNSS. And everybody has it on their phone, and to get from A to B, you actually are using the GNSS system. The finance is using the clocks. So it's space is critical. So how do we integrate small sats into that and do it in a way that if there is a problem, you don't lose your complete mission? And so how do we go about making it resilient? And I think you can do this two ways. One, through multi-satellite missions, where you spread it across the suite of small sats, but also in the design process. Granted, I'm trying to sell my particular method, but you know, so you need to have this correct through construction. But by putting in the front end, in terms of the requirements, understanding where the failures can come from, and you design that in. So it's not just me selling my idea, but I think it's part of the design process. Is you design for resiliency at the very beginning. So the approach, development of the VDP process for resilient systems, develop a capability for both at the system level, but also at each of the vehicle levels for reconfigurability. And the reason why you want to do this is because you want your system or your system of systems to have attributes of this graceful decline of capability, fast replacement and reintegration of your failed asset. This way, if I need to launch something, I already have it built, launch it, insert it, take the other one out. But also by spreading it out over multiple satellites, you're actually reducing complexity. And so what do we mean by resilient management? We're basically talking about protection, disaggregation, diversification, and distribution. And you can read what each one of those mean. And this actually comes from a larger list, but I think for small sets, these are the big four. But really what we're saying for the last three bullets is we're just talking about reconfigurability. So I want to end with this. Everybody's seen pictures of the Earth. We think of this as the blue planet. But if you actually look at this from a volume standpoint, this is all of the water. So it fits half of the U.S. This is all of the fresh water.
Okay, there's something there on the list. I see it now.
What's that?
Is that like so small? I wasn't seeing it. Yeah, I see
Oh.
it now.
And this is actually done by NOAA. So national organization, I forget what the 2A stand for.
We could use a car to go to US.
What's that?
We could drive to US, that's that map, right?
Right.
Without the water.
Right. And so I think this is my political push. Like, climate change is real, and this is going to probably be one of the big conflicts. And there's actually a group, and I can send this to you, that are actually looking at using category theory for good. Maybe that's a blog post. I'll find it, I'll send it to you, and you can.
I can spray it out.
Yeah, you can spread it out. Okay. So that's all I had.
Thank you very much.
I don't know if we have time for.
Yeah, we have some minutes for some discussion, at least. Anyone willing to ask a question? Yes, please go ahead.
In this visible light communication between satellites, how do you cope when if the satellites misalign or there's a change of trajectory? Do you have to change the directivity of your light beam, no? Or how do you do that?
So we're at the beginning stages.
Okay.
So we want to first, is this going to work?
Okay.
We think it will. Simulations say it's going to work. And one of the ways around that is because LEDs are so small, unless you're going to do an array, which is also a possibility, is that you can put it on each face of the satellite, such that
On its face. Okay.
so you can take care of those issues there, and then you can put an array of sensors also on each side. You might only want to do 4 or 5 slides, but what you can do, what's nice about space, is that once it's in orbit, it's going
It stays
to,
there.
you pretty much know when things are going to go out and when things are going to go in. Unless it gets hit with something, with the boom. That's you have a whole other issue to take care of. And so you can actually predetermine when it might go out. And then now you're designing things at the network and transport layer on how to deal with outages.
Thank you.
What is the reach of this technology in terms of transmission?
We think it'll go as far as, well, we're designing it to go as far as from 500 to 1,000 meters, maybe even pushing it to 5,000 meters.
So if each satellite is transmitting something in a sphere of 1 kilometer around itself, don't you have a lot of interference between satellites, and isn't it difficult to synchronize them so that you don't have too much errors when you are transmitting and at the reception.
So in other words, what you're saying, we have a cluster.
Yeah.
And you want to be able to communicate with each cluster. Well, this actually gets into the MAC layer protocols. And so here we're using NOMA, which we've also looked at using things like time division, TDMA, and CDMA in some combination. And so you can actually assign each satellite with a slot or a code. And that's how you get around at least that level of interference.
Okay, so you assume that you know all the satellites that need to communicate and reduce that energy in the environment.
Right.
So there will not be any issue if, I don't know, two different companies or
No, okay.
sending.
Yeah.
It's pretty.
I'm being very particular in terms of this is my cluster and I'm doing my mission. And so it's not, I don't worry about OneWeb or SpaceX or somebody else. Because if they want to come into our network, then that becomes a security issue.
Mm-hmm.
And so now how do we bring in security such they don't disturb?
But then you are reserving a range of communication, so you have one range which is yours.
Oh, it's
Well, when you say range, what do you mean?
So I mean, if no one else can communicate on that frequency, the channel is yours.
Well, it's defined in space, right? It's well contained.
Yeah.
Because the range is limited, which means that it's only available within a range of 5,000 meters or something,
Yeah.
which somehow limits the.
But you might have brought up something that I need to think about, because I'm communicating on one frequency. But
And you have not a lot of frequencies to use, right? It's just that the
I guess I could,
There are a couple of those, yes.
yeah, there's a couple of them. So I can even move, or, you know, if I'm using, can I put OFDM on there? Which there is OFDM for this. And actually, NOMA is OFDM,
And the other direction.
sort of OFDM. But anyway, at that level of protocol, then I could assign it such that it's a better utilization.
The communication between satellites is based on light.
Yes.
So, like, you should be like beamforming. You should be kind of like beamforming. So you don't have the.
No, because it's optical, I'm not going to be using beamforming. There is a way where I think I can, and I thought about that.
Yeah, we
You
really
can even use mirrors, I guess.
But the other thing is because we have a hemispherical lens,
Mm-hmm.
we don't have to, it still has to be line of sight. But I can begin to, it doesn't have to be spot on like with laser. And so that's one of the reasons why I'm pushing LED, because I don't have to be spot on. With lasers, you have to be spot on. So that's one of the attributes of this system.
It's also it's a compromise, because if you allow it to open up the ray, then the power is also going down.
Yeah.
Right.
And so it will
Right.
reduce your range.
But you know, they're developing sensors that are becoming very, very sensitive.
Sensitive.
And in fact, since coming here and working with LSDS, I believe, and I put that in quotes, that we can actually use this system for underwater communications. It's not going to be thousands of meters. But I have heard and read sensors that are basically single photon, and they're used for underwater, and if we can sort of put that in, because right now underwater communications is slow. It's acoustic. And so that could be an offshoot of some of this research. If we can also implement this for underwater.
You're saying that the sensors are improving. So do you think that your solution can, in the future, could challenge the laser communication of these other satellite constellations? Or is it still far, is very far from that?
Talk to me next year. I really hadn't thought about it.
Okay.
That, you know, if you look at it, you know, if you do a cost benefit analysis,
Yeah.
you know, there's going to be some things, some lasers are, it's going to give you the data rate that you give you gigabytes, 10 gigabytes.
Yes.
LEDs are not, though I have saw a paper where you're able to get up to 1 gigabit per second
Okay.
visible light communication on the ground.
On the ground.
I forgot what the length was, but it was a good distance apart.
Yes.
So I figure we should be able to match that in space because we have to know that.
Yes, yes.
You know, if nothing else, this should be the mode of communications and lighting when we get as we move to Mars and the Moon, because now I can not only provide broad width communications, but also light, and that's being done now. So I mean that's. But I don't know why everybody's looking at that. Even inside the spacecraft.
Yeah.
You know, to me, that would be perfect.
Yes, yes.
So do you think that the old solutions, like those that were around 20 years ago, like IRDA, could be directly used in there? Because they were actually pretty much developed at some point, but then they just lost against RF.
Right.
So they disappeared, but they are still in there. They're pretty much advanced, I would say.
And in fact, there is a IEEE standard for visible light communication. But it's more for
Indoors.
indoors. And I think that's going to happen. And the reason why is that you have so much interference, RF interference, solar interference, that affects RF interference. And I was talking with someone from Lockheed that is actually building the astronaut module. And they were just trying to get data from the tip of the solar cell into the spacecraft. And they couldn't because there was so much interference. LED's perfect. It's stationary. It's, you know, we're only talking what? At max 20 meters. Perfect. Don't have to worry about interference and don't have to worry about FCC.
So there's still a chance for all those technologies to be somehow recovered.
Yeah, and I tried to sell that to Lockheed Martin. They never got back with me. But if you see it on that they're using, I don't know if I could sue you, but I'm gonna be pissed.
Can I ask you just one more question on the other topic? So
Okay.
on the topic of design with proof by correct or correct by construction method, right? And when you do that, you typically have to define very well your requirements, and your requirements are very well known in a way that they can be somehow reproduced mathematically, right? And the problem is when you also want it to be resilient, which implies adaptivity.
Right.
That means that your requirements become fuzzy, because at some point either they are fuzzy or you have to allow ranges, or you have to widen up the space of requirements so much that then it will explode afterwards. So how do you put together this, you know, approach that is mathematically sound verifiable, and at the same time an adaptive system that will have to face,
Right.
situations that maybe were not even.
So, the way I'm looking at it is, I'm sort of not designing for autonomy, because that's really what you're describing, being self-correcting, self-healing, self-operating.
But that would be the top resilient, right?
That would be, yeah, that's like I'm going out to Alpha Centauri and I have
It will
no.
have to survive anyway.
Right. So what I'm talking about is something less than that.
Oh.
And so in terms of resiliency, as by definition, that you sort of know where your errors are going, or I shouldn't say, where your issues are going to occur. And you sort of design for that.
You have a well-defined hazard assumption or
Right.
fault assumption.
Right. You know, because that is, what you talked about is where we want to go, where I started out doing adaptive signal processing, so I was okay, what's the next step? And, how do we integrate AI? Which is another big issue that people are looking at, even in terms of resiliency, the merger of AI and cybersecurity. I don't know if we need to do that for small sats, because we're on a short mission time, 3 years. It's cost effective, so if something goes down, either I can reconfigure the whole system and know how to do that, or I'll just shut it down, send another one, integrate. And I can do that possibly in 2 to 3 months. So
But then that mechanism, the one that allows you to reconfigure, so sending new code, whatever, has probably to be formally verified.
yes,
Because that is the core that will have to be working all the time.
yes. Yeah. It's I really just got into this resiliency
Yeah.
3 months ago. This is what happens when you walk the hallway of another university and somebody says, I want you to be on this panel. Wow, it could be interesting, and then you keep running into them, and they're very forceful. So if you know anybody who's very forceful, and you can't say no to, walk away. Because they'll have you on this panel. But, in doing that panel, it actually became very interesting. I really enjoyed doing it. And, got a lot of very good feedback.
Oh.
So it's just opened up another line of research. So right now, I don't have all the answers, but I'm getting it. I'll never have all the answers.
That's the last one. Where and when do the certification authorities enter the game?
That's actually being debated as we speak, but it really should occur at the very, very beginning. Because just to get an RF license, that could take from 1 to 2 years. They're trying to streamline it, but they're also trying to make it very costly for educational institutions in the U.S. These are the new FCC groups. And so that's going to be a big one. Now, NOAA has jumped into the game. And they're offering another list of requirements and specifications that we must, or rules that we must abide by. And so right now, we're trying to fight that, to say, we can't afford $35,000 a month with $135,000 upfront fee. Where it used to be free. Now, NOAA claims education doesn't have to worry about that because they fall under section something. So in a lot of ways, this is where Europe could really sort of pass us, particularly on the education side, because they're putting too many rules in place. So, and from what I understand, I think Europe in general has basically said, you guys are crazy in the US. We're gonna do our own thing and not even worry about it. In fact, I'll leave with this. US has this big ITAR. There's a panel, head of NASA, head of ESA, and we were talking about ITAR. Head of ESA just said, we don't worry about it because by putting these rules in place, what you've done is you've made us create our own industry. And so that is how ESA has grown, how Europe has grown in the space, because they basically said there's just too many roadblocks. So we're not going to buy those parts because we can't buy those parts in the US. So we developed the industry here.
That's good, right? That's good.
That's good. That, you know,
We're happy with that.
Particularly now, if I'm going to launch something, I just work with you guys.
All right.
Buy that place in Lafayette, and I'll do it.
All right. Very good. Thank you very much once again.